Hi, this is Shaila N. Pacheco, and I'll be presenting my research work on robust face recognition under adversarial attack using Sargent model and the improved cross triple mobile net V1. This is the agenda for today's talk. Let me first introduce what face recognition is. Face recognition is the process of detecting and recognizing the faces from the image. Face recognition is very useful biometric due to its wide applications in various domains like criminal recognition, surveillance systems, security, authorization, attendance systems, and many more. With the inception of deep learning, the pattern recognition task has been very much simplified, and so many deep learning models have been proposed which extract the features automatically and perform the classification. However, the issue with deep learning model is that they are very sensitive to adversarial noise. So consider this is the original image and we are adding some perturbation to that image. So visually there is no difference in this original image and the attacked image. But the goal is that when we present this attacked image to the model, then it will classify it as a dog rather than cat. So that is called the adversarial attack. So we are adding something into image and we are making model to misclassify the data. This is the entire taxonomy of various kind of adversarial attack. We can classify it based on knowledge, number of iterations, target, and perturbation, and there are further sub-classifications of them. Due to time limit, I am not going and explain each and every of them, but this is the taxonomy of adversarial attack. This is the summary of some of the most typical adversarial attack and their principles and their characteristics. From the literature survey, we have identified certain limitations of existing work. Like accuracy is one of the problem. When we make a model error proof, or when we try to reduce the effect of adversarial attack, then there is another effect as well on the model, that the accuracy of model on clean data will also reduce. So that is one of the limitation. The another thing is that most of the work is focused on detecting the attack rather than preventing it. The complexity of the model is also one of the issue, because model will become more complex and the interpretability of the model would be lost. And the different studies may use different benchmarks, and due to that, the comparison of various algorithms would be a bit difficult. These are some of the gaps that we have addressed in our work. One is a reconstruction of the image. So after adding the adversarial noise, we have an attacked image, and we have presented an approach to reconstruct the image from the noise image. So if reconstructed image is clean, then we will get the better result. Another thing we have addressed is the overfitting. So machine learning models are often tend to overfit. So we have tried to reduce the effect of overfitting by introducing a novel weight optimization technique. Vanishing gradient is another issue in deep learning models. We have used skip connection and residual net to address this problem. And finally, for the face recognition, we have used mobile net V1 architecture, which is optimized by enhanced Firehawk optimization algorithm. The objective of our work is to develop an acceptable model for face recognition in diverse conditions against adversarial attacks. And to address this general objective, we have defined certain specific objective. The first one is to reduce the effect of attack on the image using autoencoder, and for that we have proposed a learnable convolution principal component network. So first we are presenting our image onto that immune space. The second specific objective is to minimize the noise in projected images on immune space, and for that we have a Sargent. Then next is to avoid the overfitting by finding the optimal weights. For that we have introduced enhanced Firehawk optimization algorithm. And finally, we would like to evaluate the performance of the model against diverse conditions and adversarial attacks. So this is what our entire conceptual framework is. We have created in-house database. We have captured the videos. Those videos are converted into frames. Frames are resized and labeled properly. And then we applied the histogram equalization to improve the quality of the image. And then to add the diversity into the data set, we have performed the augmentation. So from each image we are generating 7 augmented images. After augmentation, we are adding the projected gradient descent noise into, or the attack into the image. So this is the original image. This is the perturbation or the PGD attack that we are adding into this, and this is what the attacked image is. So visually it is same, but when classification is performed, it will give a great variation into the result. So once this image is generated, now our task is to reconstruct the original image from this. So for that we are using learnable convolution principal component network, and we are creating the immune space. So the task of immune space is to alleviate or the minimize the effect of this noise. And once it is done, then that immune space projected images we are using to train the generative adversarial network, that is a stacked attention residual generative adversarial network, and that will reconstruct the image. So if we look at this diagram, then this is the original image, this is the attacked image, this is the immune space projected image. You see it's a kind of blur image, and this is the reconstructed image from the GAN. So this immune space creation will give us a bit of blurry image, and this then GN will reconstruct the image from the training data. So as we can see, original image and reconstructed images are almost the same. Now to assess the performance of the model, we have conducted various tests and we have compared it on different existing models as well. So for image reconstruction, we have compared our work with the ACE, ResNet, GN and attention ResNet. Whereas for the face recognition, we have compared the performance of our model with MobileNet, VGG19, CNN and LSTM. And for the classification, we have used MobileNet V1 along with enhanced Firehawk optimization. So that will enhance the weights of the model, and it will prevent model to fall into the local optima. To evaluate the model performance, we have used various measures. Some of them are for the measuring classification accuracy, and rest of them are for measuring the reconstruction of the image. So like precision, recall, specificity, accuracy, F1 score, Cohen-Kappa score, all these measures are for accuracy measurement or the classification performance of the model, whereas the rest of all are for comparing the base image and the reconstructed image. These are the results for image reconstruction. As you can see that we have used various measures like SSIM, that is a structural similarity index measurement, then PSNR, MSE, ASR we have measured. Now SSIM varies from 0 to 1. So 1 indicates there is a perfect match. So reconstructed image is quite close to the actual image. It says 0.91%. Whereas SAE, ARN, GN, ResNet remaining existing models are inferior to our model. Similar observations we can see in PSNR. Higher the PSNR, better the reconstruction. MSE and ASR should be as low as possible. Mean squared error is minimum in our case, and ASR, that is attack success ratio, is also minimum in the presented model. So this shows that how accurately or how good the presented model is reconstructing the images from the attacked images. These are the results for face verification. So once image reconstruction is done, we are classifying them whether it's correctly recognizing or not. And for that we have used parameters like accuracy, precision, recall, F1 score, etc. And as you can see, on all parameters, the presented model is outperforming rest of all the existing models like MobileNet, VGGNet, CNN, LSTM, etc. And finally, we have compared the performance of the model across different types of image. So first bar represents the face recognition accuracy of the model on original image. The second one is on attacked image, and the third bar is after the reconstruction of the image. So it is very obvious, and we can see from the results as well, when we add the attack, the accuracy or performance measure go down drastically from 98 to 69, 98 to 68, 98 to 62 and so on. And after reconstruction, again the performance is going as high as the original image. That means reconstruction is done in a very nice way, and the classification accuracy also we are achieving very high, and that too on almost all the parameters, as we can see. So from this work, we conclude that we contribute a novel method to inactivate the adversarial perturbation for a face verification task. The proposed model proved outstanding performance in inactivating the adversarial perturbation. Also, the proposed model is optimized with a new meta-heuristic technique named as the enhanced FHO, which avoids model trapping into local minima. And the proposed model is compared and examined with existing deep learning architectures such as MobileNet, VGG19, CNN, LSTM, and it achieves the highest accuracy among all. These are the references we have used in our work. Thank you. If any question, please feel free to ask.